Okay, now we are in the next part of this chapter, and in the here also we'll learn about the basics of the electric current, and already some of the basics what we are going to learn here will be a recall of what you have learned earlier in your earlier classes. So here we'll learn about electric current, I denoted by I. Actually, to say it is strength of the electric current. Okay, now so electric current is the directed flow of electric charges. Directed flow of electric charges. It is the directed flow of electric charges. And to just define this already in your earlier classes, if you just say electric current I, you might have remembered it by the formula I is equal to Q by T. The same thing we are going to just repeat it here. So here Q is the net charge and T is the time. So how to define this? So electric current is, or strength of electric current, is the net charge through any cross section in unit time. So I is net charge is here, net charge is Q and time is T, so I is equal to Q by T. So like this we have defined. Suppose if in a conductor, in any cross section, if delta Q is the charge flowing through it in the small time interval delta T, then here one more, instead of saying it as strength of the current, now here use the term average electric current, I is equal to delta Q by delta T. And suppose if any cross section, if small current dq is flowing in a particular time, that is dt, then we use another term here, that is instantaneous electric current, I is equal to dq by dt. So now here it is in the function of the time. Okay, so now we got the definition and we came to the expression here. The same thing, I is equal to Q by T. If it is, we are talking about average, we take it as delta Q by delta T, and instantaneous means it is dq by dt. Okay, and let us talk about the units. The SI unit is ampere. Symbol is A. It is in the honor of a scientist, French scientist, Ampere. So SI unit is ampere, and the CGS unit is stat ampere. And the conversion between ampere and stat ampere is 1 ampere is 3 into 10 to the power of 9 stat ampere. And one more unit is that is ab ampere, and 1 ampere is 1/10 of ab ampere. So these are the units here. And after understanding this definition, expression and the units, let us talk about, already you might have defined an ampere in your earlier classes. So while defining ampere in earlier classes, So we just use this expression to define an ampere. So this is ampere, and this is coulomb, and this is second. So when this will be equal to 1, if this is equal to 1 and this is equal to 1. So how to define this? We define in terms of directly we don't go as ampere is so and so like that. So we just define it like this. Electric current is said to be 1 ampere. When the electric current is said to be 1 ampere, when the net charge flowing through any cross section is 1 coulomb in 1 second. So electric current is said to be 1 ampere if the net charge is 1 coulomb in any cross section in 1 second. In 1 second. So like this we will be defining an ampere. So this is the definition of an ampere. And here we observe one thing. In 1 second the charge is 1 coulomb. In 1 second the charge is 1 coulomb. And then the electric current is said to be 1 ampere. So if the electric current is said to be 1 ampere, then how many electrons are just crossing the cross section? So already you might have learned in your earlier classes about this formula, Q is equal to Ne, the quantity of charge. And there you learned that for 1 coulomb of charge, how many electrons are there? That is 6.28 into 10 to the power of 18 electrons. So 1 coulomb of charge contains so many electrons. So in an ampere, so the how many electrons will be crossing a particular cross-sectional area means it is 6.28 into 10 to the power of 18 electrons. Okay. So now pause the video and take the screenshot of this. So basing on the expression I is equal to Q by T or I is equal to delta Q by delta T, you might have did some problems in your earlier classes, just simply substituting what is the charge and what is the time, we get the extract the current. You might have extracted the strength of the electric current in amperes. And here a problem is given to you, a small numerical, just to in a different manner, just to find out the instantaneous current, the current at a particular time. So here the quantity of charge flowing through a certain cross-sectional area varies with time and is given by this equation. Q is equal to 3t square plus 15t plus 2, where t is in seconds. Find the instantaneous current through the surface at t is equal to 2 seconds. We want the current at particular time interval t is equal to 2 seconds. So now we want to find the instantaneous current. So what is the formula? I is equal to dq by dt. So what is Q here? So I is equal to d 3t square plus 15t plus 2 by t. So this is a derivative in terms of t. So you know how to write the derivations of d by dt of 3t square. D by dt of 3t square, it is 2 into 3t plus d by dt of 15t. So d by dt of 15t is 15 itself. So it is 15 and d by dt of any constant is 0. So it is 3 to the 60 plus 15. And we want the instantaneous current at surface t is equal to 0 at t is equal to 2 seconds. So this becomes 6 into 2 plus 15, 12 plus 15, it is 27 ampere. So at 2 seconds, this is the way how we find the instantaneous current. Okay. So using the expression I is equal to dq by dt, and by using the equation here, we found the derivatives and got the expression there. Okay, now let us talk about direction of electric current. So now let us talk about the direction of this electric current. Here, to say the direction of electric current, should not use the term the direction of electric current, because it is a scalar quantity. It is a scalar quantity. Here you might be getting a doubt that because the current will be flowing in a wire in a particular direction, so it should be a vector quantity. So here, even though it is moving in a particular direction, here the electric current do not obey vector law of addition. So that's why it is not a vector quantity. For example, suppose if the electric current is, here it is 5 amperes in this, and if it is another 5 amperes in this, and having some angle theta here, connected and just move like this. So what is the current in the here wire means, just we'll go with the scalar addition, that is 5A plus 5A, it is 10A. But when you go with the vector addition, you should again use, it is square root of p square plus q square plus 2pq cos theta. That is not necessary here, just simply a scalar addition can be used to add these quantities. So that's why it is a scalar quantity, because it does not obey vector law of addition. Okay, so now we understood that electric current is a scalar quantity, and specifically we should not talk about the direction, but here and there we find this, we need to express the direction of this. So here earlier, when they thought that before they found that the charge carriers are the electrons in the metals. They understood that, or they just used that, they said that is the charge will be moving from positive terminal to the negative terminal in the external circuit. That means from positive to negative in the external circuit. So if it is from positive, they just understood that it is, they just came to a conclusion that it is the charges are moving from positive to negative. And later they just found that the charge carriers are the electrons. So if the charge carriers are electrons, certainly they will move from negative end to the positive end. But already they have assumed, and because they don't want to change it, just they named this as this one from positive to negative as conventional current. Conventional means traditional, as we are following from the beginning, so it is conventional current. So here, even though the charge carriers are the electrons, and we are sure that positive charges will not move, but even then we say that, or it is said that it is the electric current is directed from positive to negative in an external circuit. Suppose if you are making a circuit in your earlier class, you might have made a simple circuit. Suppose if it is like this. So you might have shown the direction like this, from positive to negative, like this, isn't it? So this direction is called as conventional direction of the current, but the actual direction will be from negative to the positive. Okay, so like this, the direction is the direction of electric current is taken. Okay, so now pause the video and take the screenshot and just take this problem, and this is not necessary to take into your running notes. Current is opposite to the direction of flow of charges. Opposite to the direction of flow of charges. Okay. Now, after understanding this, here we talk about the flow of charges. These flow of charges are, to just keep in mind here, they are free electrons in case of metals or solids, and in case of liquids or gases, the free charges, the flow of charges means the free charges here. What are the free charges means? It's the free electrons in solids, liquids and gases, they are ions. It can be positive and negative. And there is another type, that is semiconductors. In semiconductors, there are electrons and holes. Both electrons and holes are the charge carriers. The free charges are the charge carriers. So the charge carriers are free electrons in solids, and in liquids and gases they are ions, both positive and negative, and semiconductors will electrons and holes. Okay. So after understanding this, suppose if there are n number of charge carriers in charge Q, and if E is the charge of a particle, of a carrier, a single carrier. So now what is the electric current means? I is equal to Q by T, and you know Q is equal to NE, so I is equal to NE by T. So using this expression you can find out if there are n charge carriers with the charge E, then we can go with the expression I is equal to NE by T. Now let us talk about some other different types of the current. That is steady current. Other one is the varying current, and the other one is the alternating current. What are these? Steady current, varying current, alternating current. So here you know that our electric current is having a magnitude and directed flow of charges. Electric current is having magnitude and directed flow of charges. If this magnitude is constant with time, then we will be calling this as the steady current. And if this is changing with time, we will be calling this as the varying current. And the another name for this varying current is transient current. And of course, we'll talk about this alternating current. Constant with time and steady current. Let's go with an example here. Suppose in a circuit, if we're having a resistance, then here in this circuit, the current will be steady. And if we just draw a graph between I and T, the graph will be like this. The current is constant with the time. And for example, for this transient current, suppose if we just take any capacitor in the circuit, certainly here the current changes when it is charging. So at the time we will be calling the current here will be a transient current. And if we draw a graph, the graph will be like this. So that is the transient current. And alternating current. So here if the direction of the current and the magnitude of the current, the changes uniformly with the time, then we will be calling the current as the alternating current. So you just draw a graph like this, I, and T. So the direction changes and the magnitude changes. So the magnitude goes to maximum and minimum, maximum and minimum, maximum and minimum. And the magnitude changes like that, and direction will be, once it will be one direction, other time it will be in another direction. We will be calling the current as the alternating current. So an example for this is, if you just keep an AC generator, this is a generator, AC generator in a circuit, then we can see the current is alternating in this circuit. Okay, so this is regarding the different type of current: steady current, varying current, and alternating current. If the magnitude varies with the time, we will be calling it as the transient current, and if it is constant with the time, it is the steady current, and if its direction and magnitude is changing, then we will be calling this as the alternating current. Okay, so now here we came across those certain things here. That is, we came across an expression that I is equal to NE by T. Where N is the charge carriers, and if E is the charge, then we can use the expression I is equal to NE by T. Okay, now pause the video and take the screenshot of it. Okay, now let us understand the another basic things, what you know already about the different substances. You just call them as the conductors, insulators, and the other one is semiconductors. So depending upon the conductivity or the conduction of the electricity, we can divide the materials around us into three categories as conductors, insulators, semiconductors, basically. Okay, right. Now, what are these conductors? As you know the definition very well, which allows the charges to flow through them. Okay, and now insulators which do not allow the charges to flow through them. What are these semiconductors? Already you might have understood about this or known about the semiconductors. Their conductivity lies between conductors and insulators. Conductors and insulators. I'm coming with the examples here. Conductors. Our human body is a good conductor. Human body. And earth is a good conductor. And you know, all the metals are the good conductors. And acids, bases, salts. So these are the examples for the conductors. Insulators. We talked about air is an insulator, and dry wood, not the wet wood, dry wood, and mica is one more important thing what you should keep in your mind. Mica is a bad conductor of electricity and a good conductor of heat. So that's why it is used in some of the electric appliances, because it won't conduct electricity but it can transfer the heat. Okay, so rubber, glass, pure water, like that. And semiconductors, germanium and silicon. So these are the examples for these semiconductors. So now we understood the definition and some examples. Now let us understand the difference between the conductors and insulators. Insulators by the term of free electrons. What are these free electrons? These free electrons are the electrons which are not bound to any particular atom. So these are free electrons or the electrons which are not bound to any particular atom. Any particular atom. And here, when we talk about these conductors have the availability of free electrons in them. Have free availability of free electrons in them. And if you consider any cross section of this conductor, this free electron density will be same. The free electron density is constant at any cross section of this conductor. Just keep that in mind. Now here, suppose if it's in a conductor, already we said that some free electrons are there, and these free electrons will be moving at random. Already you understood about this, will be at random, and the net flow is considered as zero before applying the potential difference. Suppose if you are just injecting a free electron into it, this free electron will move into this conductor, and it cannot stay together with the other, or it cannot stay with the other free electron present in the conductor, because the electron repels. So this starts moving. So these free electrons what are introduced into the conductor starts moving. So that is why the conductors are able to conduct the electricity, or allow the charges to flow through them. Okay, so so like this we can talk about the conductors, and we understood that because these charges are whatever we have introduced into the conductor, that introduced free electron will not stay there itself, because the free electron there repels it and it starts moving ahead. So thereby the free electrons will be in continuous, they will be in motion. So at a particular instant, so on a particular surface here, the free electron density will be constant. Okay, and coming to these insulators. There is no availability of free electrons in this insulator. So if you just take an insulator and if you introduce a free electron into it, whatever the free electron introduced there, it stays there itself. It cannot move ahead. And if you want to make it move, you have to apply high voltage, which increases its kinetic energy, and thereby it can move. So by applying very high voltage, sometimes which it is not practically possible. So at that particular high voltage, the free electrons there will gain the kinetic energy and starts moving in the insulator, and there it can produce electric current in small quantities, very small quantities. Here we took just examples as air, rubber, glass, all these things, isn't it? So here you might get a doubt that how we can able to see the lightning in passing through the air. So there you know already that the lightning, which is at a very high voltage, make this air to conduct. As I said here, high voltage provides the kinetic energy sufficient to these free electrons, which makes them to move. So here for the insulators or dielectrics, whatever you want, you can call them as insulators or dielectrics. So if you are able to provide a high voltage, we will be calling it as threshold voltage or breakdown voltage. Then it can allow the charges to flow through it. For it is expressed in kilovolt per millimeter. This breakdown voltage is expressed in kilovolt per millimeter. And if you just take for the example of air, the breakdown voltage is taken as 3 kilovolt per millimeter. So if it exceeds 3 kilovolt per millimeter, then it can conduct then it can allow the charges to flow through it. And we can take one more example here. You might have observed when you are moving near the high voltage lines, HT, high voltage, HT lines, high tension lines, they will be hearing a hissing sound. This sound will be coming. So why that hissing sound is there? Because when high voltage is passing through these wires, the oxygen around it will be broken, and due to this reason that hissing sound is coming. This oxygen broken there will combine with, that means the nascent oxygen formed there, combine with oxygen forming the ozone, and if further more high voltage is provided, then it can conduct the electric current. And talking about the semiconductors, you know that in semiconductors the charge carriers are the electrons and holes. So we will learn about this completely in a separate chapter, electronics, about these semiconductors. And this is regarding conductors, insulators and semiconductors. And now we talked about the differentiated the conductors and insulators in terms of the free electrons. Okay, now we'll just go with a new term, that is current density. Current density J. What is this current density? That is the electric current per unit area. The electric current per unit area. Electric current I per unit area. A is the current density, and J is given by I by A. So here electric current is a scalar quantity, but J is a vector quantity. J is a vector quantity. So I can represent it by J bar. If J is a vector quantity, then what is the direction of J? So the direction of J is in the direction of electric field E. So J and E are having the same direction. That means if we consider the direction of the positive charges, then your J will be in that direction. If you consider the negative charges, they will be